that even possible? Like, I'm sure he'll be okay. Okay, let's go figure this out. Okay? Okay. Presenting Indiana Jones and the impossible equation. So we figure the wall is about 4 meters high, and it's been falling for about 3 seconds before Indy realizes that he's lost his hat. So, using the velocity equation, VW equals 1.5 to the 2t minus 3, we need to figure out exactly how many seconds he has left before the wall completely shuts him out. First, we need to find the antiderivative. So, we know since we have an exponential function, the antiderivative is 1 over the derivative of the exponent, which is 2, times the ln of the constant variable, which is 1.5. All multiplied by the original function, which is 1.5 to the 2t minus 3. Now, using the fundamental theorem of calculus, we need to integrate from 0 to t, which is the total time it takes to fall, to find out how many seconds it takes for the wall to fall all the way down. So we have to use our antiderivative of the first variable, which is t. So it's 1 over 2 ln of 1.5 times 1.5, 2, and t minus 3, all minus the antiderivative of the lower variable, which is 0. So we have 1 over 2 ln of 1.5 times 1.5 to the 2 times 0 minus 3, which is pretty much just going to give you negative 3. When we integrate this, we get a total time of t equals 5.214 seconds. This is the total time it'll take for the wall to fall the full 4 meters. But as you remember, it's been falling for 3 seconds already, so we have to subtract the 3 seconds from that. And we get 2.214 seconds left until his hat is just gone. See, Mike, I told you he'd be okay.
Oh, thank God, I'm so relieved. I was so nervous I had to go change my shirt, but now I'm all dry. I'm better now.
I wonder how fast he was going.
I don't know. Now that we've found the time it takes to get under there, let's write an equation for his hands a lot easier. So since we know that t equals 2.214 seconds, and it's given from the movie that his hand starts about 0.2 meters away from the wall, and then the hat is about 0.2 meters away on the other side of the wall, and then he needs to get back to the wall before it shuts in 2.214 seconds. So that gives him a round trip of about 0.6 meters that his hand needs to make. So the best way to model this function is with the sine, because, as shown here, the velocity starts at 0, increases, slows down as he's coming near the hat. When he hits the hat, it's going to reverse direction, come down, and his velocity is going to be negative again. So we know that he needs to be back halfway through with the hat before he gets to 2.214 seconds. So, before you get here. And that we also know that since this is right in half, that each one of these parts is an even third. So all we really need is the top up here. So we're going to do 2/3, because each one of these is a third, 2/3 times 2.214 seconds, and that is going to give us 1.476 seconds. He needs to go, or hit the time he has to reach the hat. And in that time, he's going to need to travel 0.4 meters. As you know from calculus, 0.4 meters is the area under the curve up to this point. So, from here, the basic sine equation looks something like A sine of B times T. So we need something that looks kind of like that. So, as we stated before, 1.46 seconds is right when his sine equation equals 0 right here. So we need to get sine on this side to equal 0, because that will cancel out this constant here, so we can solve for b. And the only way sine is going to equal 0 is if we get pi in there. So we have to have something that sine of bt equals the sine of pi, which is 0, or bt equals pi. And we know what t is at this point because we just solved for it. So we need 1.476 seconds times b equals pi. Divide that over, and you get x, or b, to be 2.128. So we have b, and we got to find a now. And I said before, he's just going to travel 0.4 meters in there. So from 1.476 seconds to 0, from here to here, he's going to need to travel 0.4 meters. So to do that, we're going to use this original function up here. So we got a sine of, since we just solved for b, we're going to do 2.2128 times our t, and we need, dt, we need that to equal 0.4 meters. So we're going to do the definition, or the fundamental theorem of calculus to do that, and so we're going to need to find the antiderivative of this function in here. So the antiderivative is going to be a, because it's a constant, stays the same. This is going to come out, so it's going to have to go on bottom. 2.2128 is going to be on bottom here. And then it's going to change to cosine, and it's going to become negative on the outside. So cosine of 2.218. And we're integrating from b to a, so b goes in first. So we're going to put 1.476 seconds in. We're going to subtract the same equation, but with 0 plugged in, so it's going to be a plus a over 2.218 times cosine of, and since this is 0, it's going to make the inside 0. 2.218 times 0 is going to be 0, so we should put 0 in there. And we're going to have to solve for a, which is going to equal 0.4 meters on this side. So when we solve for a, it's fairly easy. Cosine of 0 is going to be a positive 1. Cosine of pi is going to be a negative 1 on top. So you get the negative 1 cancels out this, so you end up with a over 2.218 plus a over 2.218, and that's going to equal 0.4 meters. Solve for a, and you get a to be 0.4256. So, after all that, we get our final equation of Indiana Jones hand velocity to be 0.4256 sine of 2.218 t.
Mike, you're such a worrier. This is why you need to take calculus.
I know, it soothes my soul.
And you can figure out real-world problems like Indiana Jones' velocity.
I think everybody should take calculus.
Me too! Okay, 1, 2, go.